we need to look at the history associated with our knowledge of subatomic particles and their world. So that's what we're going to spend the majority of our time building up our case for the historical aspect and finishing off this section today by taking a look at, where we really started to dig our feet in and gain knowledge and ideas regarding contemporary models and ideas of an atom. So we start off with the philosophers, right? So early philosophers, they questioned everything. They first thought that matter was composed of earth, water, air, and fire. Some of the most common and, at the time, essential forms of material that they knew of and that was useful to them. The problem about early on experimentation was the fact that those running the experiments lacked controlled experiments. Now, that term controlled experiments is nothing new to us. We learned about it early in the semester. Okay? When you have controlled experiments, you control every aspect that is possible in an experiment so that you can identify what is causing the result. Okay? The reason for this is because they had very few tools for scientific experimentation. So they had to speculate in order to create theories. And use those brains of theirs to make educational statements about why things were. Many also believe that matter could be endlessly divided into smaller and smaller pieces. So that statement has both correct and incorrect information in there. Okay? Yes, matter is made up of really small pieces. Again, they didn't know that. But they said they could be infinitely divided, endlessly divided, which that's where they are incorrect. I'll start off with some of the first philosophers here. We have Democritus. From 460 to 370 BC was the first person to propose the idea that matter was not infinitely divisible. So now we're starting to get on the right track of our current knowledge. Many, many, many moons ago. Okay? Philosophers believed that matter was made up of individual particles called atomos. Wonder where we got the name atom from. They thought that matter could not be created, destroyed, or further divided. So Democritus is really onto something way back in the day. These are still concepts that we call laws now. Again, he had many more ideas as well. Okay? Whole box of ideas. From Democritus, we go through to Aristotle. There's maybe a name you've heard of before. 484 to 322 BC. Yes. Aha, Jesse. What have you been writing with so far? Your fingernail? Well, good thing I'm recording this session so you can go back and get it filled out. You might have time at the end to fill it out as well. So Aristotle disagreed with Democritus' thoughts on matter. We're gonna have a fight. Aristotle did not believe that empty space could exist. Big thing to fight about, empty space. So he began to question what was holding the atoms together. But Aristotle, being at the stature and status that he was during this time, his views went unchallenged for almost 2,000 years. Until science developed methods to test the validity of his ideas. Okay? He was one of the most influential philosophers. I guess you kids would call those influencers now, right? Right. So, again, 2,000 years. Don't do the math. 484 to 322. 2,000 years after that. In terms of history, that's right there where we are currently. So, the world really didn't change their notions for quite a while on this. That's when John Dalton came in. So, Dalton was a very important figure when it comes to atomic theory. Was this stuff perfect? No. But at the time, it worked. Because as the history of science goes on, we have models, we study models, new technology comes about, we restudy models, we evaluate and adjust our models accordingly. So, Dalton was simply a school teacher from England, and he revived and revised Democritus's ideas based upon the results of scientific research that he conducted. Now we're starting to get more and more of those controlled experimentations coming about, new technology that allowed for us to start revisiting some of those classic, if you will, ideas from the early philosophers. And his work marked the beginning of the development of our modern atomic theory. We often refer to Dalton's what we call postulates. And we're going to learn about Dalton's atomic theory, Dalton's postulates, here in this first section. All right. So, his first part of his theory was that matter is composed of small particles called atoms. Again, Dalton revisited and revised Democritus's ideas, where Democritus called small particles atomos. So, kind of paying homage to Democritus here by calling them atoms. The next postulate or portion of his theory was that atoms of a similar element are identical. Atoms of other elements are different. Now, this second statement is, for the most part, true. There were a few things that he didn't know about when talking about this second, where he says atoms of a similar element are identical. In some ways, they are true, yes. In other ways, they are not. Okay? Again, they are similar in the fact that atoms of the same element will always have the same number of protons. There's no getting around that. However, during Dalton's time, there was not the notion of what we call isotopes, which are slight variations of a particular element, still retain some, nearly all the properties of that element, but they can fluctuate slightly from atom to atom. The third postulate is that atoms cannot be created, destroyed, or divided into smaller particles. Again, took Democritus's statement, showed that half, or he theorized that half of that was true, but then he said, well, the part of Democritus said that it can be broken down further, and we really can't. It comes to a point where we cannot go any smaller, but yet we cannot create nor destroy atoms. And in chemical reactions, atoms are separated, combined, and rearranged. That's why we get new products. when we have a chemical reaction. It's not that we are simply creating them out of thin air. We're just simply taking the atoms, rearranging them, forming these new products. But we are not creating things. We're simply rearranging atoms. So, Dalton came up with this theory based off of scientific research. And so what he did was his scientific research was based on numerous detailed experiments where careful observations of chemical reactions were taken. And so by doing so, he was able to accurately determine the mass ratios of the elements involved in the reactions. And so by doing so, this easily explains the conservation of mass that we talked about last chapter, the chapter before that. It stated that this conservation mass was from the separation, combination, or the rearrangement of atoms. Tristan, roll out of your pocket. And as we stated that throughout this process, the atoms are not created, destroyed, or divided in the process. And evidence of the conservation of mass from Dalton's experiments provided a clear explanation of the composition of compounds. And so all this scientific research that Dalton conducted provided a general acceptance to his atomic theory, therefore the existence of atoms. However, if your scientific work is good work, it's always going to raise new questions. If it's bad work, it's going to say, why did you even do that? It's not even correct. But when it's good work, and it gets the community talking, gets the community asking questions about what next. If we know this and this is accepted, where do we go from here? So the questions arose like, what is an atom like? How are atoms shaped? Is the composition of an atom uniform throughout, or is it composed of still smaller particles? Again, good work leads to great questions. So then we start looking at the atom itself. It's the smallest particle of an element that retains the properties of that element. A single atom of oxygen is going to have the same properties of the entire, however many elements of oxygen there are. If you have a pound of steel, a pound of iron, a single atom from that pound of iron is going to have the same properties of all the other atoms in that pound of iron. We look at a gold ring. If we were to grind a gold ring into a pile of gold dust, each fragment of gold dust is still going to retain all the properties of gold. So we continue to divide the gold dust particles into smaller and smaller particles. And then a single atom of gold is going to occur when the particle can no longer be divided any further, but yet still retain the properties of gold. The moment that you get where you cannot divide it and retain properties of that element, you are currently at the atomic level. So, a lot of the early philosophers couldn't quite support the idea of atoms, and it wasn't until a few hundred years ago that it was generally accepted. People saw the idea, the question was like, well, why can't we see them? So the size of atoms, as you can imagine, as you already probably know, are very small. Atoms can range from the diameters of 1 times 10 to the negative 10th meters to 5 times 10 to the negative 10th meters. In fact, the atomic scale or atomic size, the atomic unit that we use to measure size of atoms is called an angstrom. It's got its own unit when we start talking on the atomic scale. Now, we've all seen a copper penny, okay? But if you're looking at a copper penny, no, it's not that very big. It's like, I don't know, that big or so. Within a pure copper penny, which they don't really make anymore because copper is a very hot commodity, and so they use alloys and everything like that. In the times of a pure copper penny, there were 29 times 10 to the, what was it? 29 times 10 to the 21st copper atoms in a penny. Just a single penny. I don't even know what number that is. I'm sure it's got a name. Probably wouldn't be able to pronounce it myself. But still, that is how small atoms are. In my honors class, when we're looking at and calculating the size of atoms, if you were to take your pencil, draw a single line with your pencil, and we were to look at and measure the diameter of that line that you drew with your pencil, there would be, I think, over 6 million carbon atoms, maybe more, 6 million carbon atoms side by side across that single line from your pencil. Tiny, tiny things, okay? Now, we can see atoms. Again, it wasn't until the development of technology where we have a scanning telling microscope, or what we call STM. It's an instrument that allows individual atoms to be seen. Now, because of the advancement in this technology, we can now advance other technologies like nanotechnologies, nanocomputers. You watch movies that talk about nanobots. Okay. Nanotechnology is still relatively in its infancy, but it is making great progress all the time. And a lot of experts are saying that this nanotechnology will be the wave of the future that will actually utilize nanotechnology within our cells or other places on Earth, and we can use them to better ourselves, make ourselves healthier in certain ways. I mean, the ideas are really at the time they kind of just open. Okay, so that is it for section 1. A nice little history about the development of our early understanding or lack thereof of atoms, kind of how the idea of atoms came about, and then taking a huge break from even questioning it, thanks to Aristotle. And now here we are today talking about nanotechnology. Tomorrow, you will have your homework check. Okay, so make sure, Jesse, do you need some more notes, to copy more notes? Okay, I'm going to stop the recording here.